Okay, and you can just click got it on that one. Oh yeah. Got it. And then we'll go to Zoom. Hello, everyone on YouTube. We're getting started here. Let's go with this. Christine's on. Hello, Christine. We can do this recording to the cloud. And excellent. All right. So welcome, everyone. Then click got it over there. It is my pleasure to introduce today our speaker, Dr. Jennifer Sagan. Jennifer Sagan is a senior project manager and associate scientist at WSP USA, which is a big consulting firm.
Yes.
More or less. And she can
Used
tell
to be wood.
you can tell us more about that wood and Amos Foster Wheeler and all that. She has more than 20 years experience monitoring and restoring aquatic ecosystems in Florida. And she leads both engineering and scientific teams. We talked a little bit about the difference between an engineering team and a scientific team in ecological target setting, coastal modeling and restoration design, and including, I don't know how much you'll talk about, but dealing with the whole permitting issue. So I don't know if you'll talk about that today.
A little bit. That's not my bailiwick, but
Okay.
I do have some insights.
So we'll go ahead and share this and that. Hide these and minimize this. And is that working?
Can I go back one?
Yes. One second.
not
And now it should work. Yep, you should be good now. There we go.
There we go.
All right. So Megan, give me a chat when you know YouTube was up and running, but I think we should be good. And the floor is yours.
Oh, okay,
Yeah.
great. Well, thanks for the invitation. I'm excited to talk about this project. This is actually a project we worked on with Dr. Christine Angelini. She's the lead PI on it. Actually, I'm gonna use past tense because we completed this project. But really want to talk about more of the planning aspect. This was the feasibility stage of a thin layer placement of dredged sediments to restore and provide resiliency to salt marsh habitat. And in addition to the WSP project team, as I mentioned, Dr. Angelini's team were leading the project, but we also worked with the Guantanamo-Matanzas National Estuary Research Reserve, and I'm just going to refer to them as the GTM NER from now on. FDEP folks that were stationed at the NER worked with us as well, and the City of St. Augustine. And just to give you a little background on kind of the genesis of the project, 5, 6, 7 years ago, a colleague and I were attending a conference at the GTM NER, and the then director, Mike Shirley, was mentioning that they were seeing that their salt marshes were not accreting sediments that at a rate that were keeping up with sea level rise, and they were noticing drowning effects in their salt marsh. And he had heard of this technique called thin layer placement and wanted to look into that as a way to restore their marshes. And it just so happened that our company utilizes this technique not only for salt marsh restoration, but for other applications. So we approached them about their interest. And then they said, by the way, you should talk to Dr. Angelini because she's actively working in the GTM NER, looking at the erosional effects of boat wakes on the fringe margins of the salt marsh habitat and how using these semi-permeable barriers reduces the wave energy and actually induces progradation of the marsh behind these barriers. So we started thinking about, this project and where we might apply it in the GTM NER. Before I go on, though, I did want to kind of do some definitions. When you hear the word thin layer placement, in my mind, when I hear thin, I think, something maybe this, a depth or thickness like that. But when you read case studies of thin layer placement, it can mean 15, 30, upwards 60 centimeters of application of sediment in a salt marsh. So you have to kind of rethink what thin means. Another thing is we often think about this picture of the technique for dispersing the sediment, kind of a pivot irrigation idea of where it rains down in little bits. But in fact, this pipeline where you could have a 12 or 16-inch wide pipeline where you're adding basically a controlled slurry and then letting it disperse is also considered thin layer placement as well. So just kind of wanted to get everyone's head wrapped around if you have any preconceived ideas. And well, we didn't design this, come up with this on our own. There's a lot of precedent for both of these techniques, the thin layer placement as well as the semi-permeable barriers. The Army Corps has about a manual where they outline 29 case studies Most of these thin layer placement applications have occurred in Southeast United States. A lot of work is being done in Louisiana. But also the National Estuary Research Reserve, about 9 different NERs collaborated, and they did kind of a summary and guidance document showing successful projects using thin layer placement. And then, as you can see, a lot of work using breakwalls for mitigating that boat traffic wave energy. So the reason this project was of interest to us, not only because the GTO NER was very interested and saw some localized impacts due to sea level rise and other anthropogenic impacts, but it's a project with multiple benefits. So in Florida, increasingly, we're seeing the effects of global warming in terms of sea level rise, increased frequency and intensity of storm surges. And so when you look at Tallahassee right now, they're requiring municipalities to come up with coastal resiliency planning documents. They're putting out a lot of grant money to fund coastal resiliency projects, and they're really putting an emphasis on green infrastructure using living shorelines, whether it be oysters or salt marsh or corals or mangrove, whatever. Then couple that with, in Florida, we've been spending many decades now trying to correct sins of the past. We didn't know any better. And we, built on top of salt marshes, we dredged through them. We basically have really negatively impacted a lot of our coastal ecosystems. And there's a lot of work going on to restore them, because we understand not only do they provide protection to coastal infrastructure, but ecologically they're invaluable. And that ends up translating to economically invaluable when you look at the fishing industry or the seafood industry, et cetera. So we've got that going for us as well, a lot of interest. And then finally, the third peg in here is that the Army Corps of Engineers and the Florida Inland Navigation District are responsible for dredging and keeping navigable our navigable channels within Florida, our ports and passes and things like that. They're increasingly, though, as they dig out these sediments, are having trouble finding places to store them. There are upland dredge material management areas that are running out of room, and there are ocean disposal sites that they're running out of room as well. So they're asking folks, please come up with some beneficial reuse of the sediment that we've been dredging. Let's reuse it. Let's keep it in the system. And that's really what this project does, all 3 of those things. So we chose a site location in St. Johns County, which is along the Atlantic seaboard in Florida, and specifically in the city of St. Augustine. And if you know St. Augustine, I'm not going to press a button. I'm afraid it will.
Let's see.
Will that make a little pointer?
Does it look like?
I'm not going to do that.
I think
I'll just point. North of here is the old historic district of St. Augustine and the Bridge of Lions, if you know that.
Yeah.
This is the intercoastal waterway. At this point, it's called the Matanzas River, and that is San Sebastian River. And then you got State Road 312, and the salt marsh here obviously was degraded. We also see, though, that it has potential, is protecting or has potential to protect some really important infrastructure. The only hospital in St. Johns County, or in St. Augustine Flagler Hospital, lots of residences. This is another hospital complex over to the right. That State Road 312 is an evacuation route. And then later, it's kind of blocked out, but you can see it. There's a wastewater treatment plant, and it wasn't part of our initial red outlined project area. But later on, through stakeholder meetings, our stakeholders said we need to push that project up there as well to include protection of that water treatment plant. So really a lot of important infrastructure that the salt marsh potentially could protect. So we pulled together a proposal to submit to NIFWF, the National Fish and Wildlife Federation, Federation, one of those, for a feasibility grant to conduct the salt marsh restoration planning, basically, and come up with a conceptual design. It was Dr. Angelini's group that did the historical rates of salt marsh and shoreline change. DEP hosted all the workshops with the agencies and the stakeholders. WSP, we did the salt marsh and intertidal habitat conditions, but also worked with DEP, who flew, you'll see some at the end, some beautiful drone imagery they grabbed that we didn't get to use this time, but we'll use in a phase 2 if there is one. WSP, we did all of the dredge and sediment application and constraints. And we also produced a preliminary design document, conceptual design, and we submitted that just in August. So let's dig into what was the actual problem that we're seeing. As I mentioned before, the first 3 represent what were already existing lines of evidence of salt marsh loss. The GTM NER had these sediment elevation tables where they showed that the marshes were not accreting sediments at a rate that kept up with sea level rise. Silman and other researchers were looking in St. Johns County, and again, that both weight traffic issue. They were seeing lateral erosion of up to 1 meter a year in the salt marsh. And then Dr. Nikki Dix at FDEP and others documented the loss of a net loss of over 9,000 acres of salt marsh in Northeast Florida. And then locally, for our project, Dr. Angelini's team looked at and did photo interpretation of 2005 all the way to current day aerial photography to confirm where and how much shoreline retreat and marsh loss we were seeing. She also deployed terrestrial laser scanning that not only shows reduction of or movement of the shoreline retreat, but also measures changes in height of that shoreline as well. And then WSP, we went back to 1952 photography and did some photo interpretation of the salt marsh footprint. We saw a loss of 100 acres. We ground truthed low vegetation areas and confirmed that these were drowning low density areas. And then with off-the-shelf LiDAR confirmed that there was an elevation difference there as well. So to dig in a little more closely to some of the data, I won't be able to show all of it, but this is more telling a picture of kind of what we did to go to the stage of design and figure out where and how much sediment to add. So as you can see, there is a net loss really of marsh just since 2005 in what Dr. Angelini's group identified as 6 zones. This is the original footprint that I showed in red before. There's another zone 7 and 8 now. And if you notice, zone 1 and 6 really show the greatest amount of marsh change. So we decided to concentrate on those 2 zones in terms of our data collection. We'll also use that other data, by the way, later in phase 2 to really look at what some of the processes, sediment transport processes might be in the area to kind of get a feel for what's happening there and where we might be able to place sediments. And then we also, as I mentioned, looked at 1950s aerial photography. This represents that new zone 7 and 8 that we added. And in the 1950s, the total marsh in those 8 zones totaled 350 acres. Current day, we're at 250 acres of salt marsh habitat. So quite a bit of loss in that area. Oh, let me go back. And then if you focus just on zone 1, if we blow that up, you kind of get a better feel. The black represents the current footprint of the salt marsh. And the hatched area is where there used to be salt marsh grasses in the 1950s. So habitat sampling. As I mentioned, we want to concentrate our data collection in zones 1 and 6. And so we collected vegetation data, took photos at 36 of our study plots. DEP flew all over the site, not only zones 1 and 6, but all the others. We collected vegetation samples and looked at stem densities and widths and heights. Applied the Blanc-K density scoring method, collected sediment cores, and georeferenced all of this work. We didn't randomly place our plots. We decided to strategically place them to answer some questions that we had about the aerial photography and some of the things we were seeing. First of all, we knew that the dominant species was Spartina, so we really focused our efforts on capturing study plots that were the Spartina alterniflora. We also noticed, though, if you see one of these islands here, see how it's much darker there? That looked to us like the density of the vegetation was much greater than in these areas here. But in addition to a density difference, it also looked like this was at a higher elevation. So we really wanted to make sure that our plots were placed in different locations so we could kind of ground truth that aerial photography interpretation. And so when we went out there, we looked at Blanc Blanquet covers for the total plot, individual species, and we did run into mangroves. We didn't emphasize them, but we did capture some mangrove data and measured width and height of those plants. And sure enough, when we looked at the photography and went out there, you can see that when you have very sparse vegetation, it does correspond to these areas in the center, and our dense, lush Spartina plots do coincide with the darker areas that you see here. In addition, the off-the-shelf LiDAR confirmed the elevation differences. You can see you have higher elevations around the edges. We do see some drowning and lower elevations here. And then, of course, we don't have LiDAR from the 1950s. However, anecdotally, you can see back in the 1950s, there used to be salt marsh habitat there. Now it's mud flat at a very low elevation. That currently does not support Spartina. And if there had been Spartina back in the day, it's an indication that there was a greater volume of sediment at a higher elevation at that point. So there's been some sediment export at the site. And we didn't have a lot of data, so I couldn't do statistics on this, but just to give you an idea that we did see differences in elevation, again, off-the-shelf LiDAR for the highest density rating compared to the other ones in the salt marsh. So something's going on in terms of plant, when the plant is growing at its most robust in elevation, sediment elevation appears to play a role in that. So once we collected some data and wanted to talk to the stakeholders about the next steps, we did hold actually two or three different workshops, and really got some input from them. You can see all the participants, a lot of the agencies, as well as local municipalities and some riverkeeper groups and things like that. And basically, as we discussed the challenges and the possible remedies and what our goals ought to be, we ended up coming up with project goals that focused, how our design was going to look. And first of all, everyone said, let's expand that retreating marsh back to that 1950s footprint. Let's add sediment to give a elevation lift to those areas where we see the interior drowning occur. Let's also be mindful of predicted sea level rise, that we might build it up to a certain level where the plants are happy and elevation is keeping up. But eventually sea level rise, as we know, is occurring at a rate that outpaces that sediment accretion. So maybe let's also give a little elevation lift and add a little more sediment, just knowing that sea level rise is going to continue. Convert the existing wildlife habitat, meaning the mud flats and the oyster bars, back to that salt marsh that we know was there in the 50s. And the interesting thing about the salt marsh, why do we say that it protects infrastructure? Spartina alterniflora, and this is true of mangrove and some other salt marsh species, but it is very good. And actually, FEMA has a model that if you input the stem density, the stem width, the stem height, and the acreage, you can calculate the wave height mitigation that you get from that salt marsh. So we can quantify that certain sizes and densities of salt marsh will actually reduce flooding due to storm surge. So very protective of coastal communities. And then finally, our last goal is let's use locally sourced sediments. And so we pulled all of that in, and this is our solution so far. So again, using the sediment application via thin layer placement, using intercoastal waterway sediments, in other words, those dredged from the Matanzas River and further up, and use them in conjunction with the semi-permeable breakwalls. The first step, though, is where do we get the sediment? Initially, we had a lot of discussions with FIND, the Florida Inland Navigation District, about trying to sync up our project with their dredging operations. And what that would have required for this feasibility stage is that they knew they were going to dredge, and they were out there collecting their own data that we could use and look at the sediment and see if it was appropriate, both ecologically and for an engineering design. We couldn't sync up. So instead we pivoted and we started looking at potentially pulling sediment from the dredge material management areas. And as you can see here, from Duval County all the way down to Flagler, they have, what is this, 2, 4, 6, 8, upward 10 different dredge material management areas. These are just gigantic reservoirs that are holding the sediment that are dredged from that intercoastal waterway. And the one closest to our site, 18 miles away, SJ14, was designed to hold upward 2 million cubic yards of material. There are a lot of users of this, developers pull it out, but you know, even when it's at lower capacity, this is 800,000 cubic yards is way in excess of anything we would need for our site. So this was a good start. We knew we had volume and a fairly close source, and it was coming from the very intercoastal waterway that abutted our sediment, our site. The next step is to look at sediment and how it matches the donor sediment. I'm going to call the intercoastal waterway sediment the donor sediment. How well does it match with the sediment we saw that we collected from the salt marsh? So again, we collected from zones 1 and 6, and then we also collected from the dredge material management area. Now you'll notice we collected in a really tiny area, and this is because they had an active excavation going on at the site. And we were not allowed to go elsewhere. Also, because of project constraints, we only collected to a depth of 3 feet. When we redo this, we would go back there and we would take cores using a drill rig from throughout and go down to the depth. This goes down to 10 or 15 feet because that's where potentially we would excavate to pull out material. To get a better feel for this. But for now, let me just tell you what we found and what the implications later on might be.
Jennifer, just so for those, this is literally just like a giant sort of pit. You drive by it on some road and it's just full of stuff that they pulled out of the sea or the intercoastal waterway and just leave there. Water drains out of it. And
exactly.
The material is just like, hey, what can you do with this stuff? So, so if you haven't seen that before.
Yeah, and it literally, when you walk up, you look up and it's almost the berms that hold it in are about 2 stories high. It is gigantic and they have big dump trucks. Yeah, I should have done it to scale. A dump truck would be about the size of one of those dots. That's how big that is. Yeah, it's huge. Yeah. So what we did is we took our samples both from the salt marsh and the dredge material management area and did chemical analysis on it, as well as physical analyses. And actually Dr. Todd Osborne at the Whitney lab handled all the physical analyses. The chemical analyses were the typical pollutants of concern that we want to look at. That DEP, one of the permitting agencies, probably wants us to check out. And so let me go over the chemical results first. First of all, so Florida Department of Environmental Protection wants to make sure that if you're adding something to an environment that it meets ecological as well as human health criteria. And I don't know how many decades ago, they developed a marine sediment quality assessment guideline. And this is a compilation of data from a ton of different laboratories and field experiments. And basically it sets what's called a threshold effect level, or a concentration for a ton of different PAHs, heavy metals, other contaminants. And they did tests to show that if you're underneath the threshold effects level, that the macro and micro benthic organisms at that site are probably not going to be affected. They've not shown effects. But if you have concentrations that exceed that TEL, then you might see negative impacts to the biota of that site. Similarly, for human health, there's a soil contamination threshold for residential. And this is if like you were going to take this sediment and build homes on top of it or build a playground or something. You want to make sure people coming in contact with that soil are not coming in contact with contaminants that would adversely affect humans. So we use those 2 criteria. And the good news is we only, out of all of those PAHs and heavy metals and petroleum products, we only got a hit on 2 analytes or contaminants that exceeded either of the thresholds. And the really good news is they didn't come from the donor site. The dredge material management samples were really, really clean. Any exceedances we got were actually in the salt marsh. Now, I'm cheating a little bit though. Well, I'll talk about this in a second. Remind me to come back to why I don't expect to get that good a result when we sample the other parts of the DMMA. Another thing we looked at was nutrients. DEP does not have nutrient criteria for sediments. They do have numeric nutrient criteria for surface waters. However, we know that if you add sediments that are laden with nutrients, there's going to be uptake, or you're going to see some water quality effects in the water column. So we want to make sure we weren't adding something that just had a ton of nitrogen and phosphorus in it that could cause potentially an algal bloom. And good news again is the dredge material management values came right in between our salt marsh values. So looking good so far. Yeah, so we have a really good ecological fit there. We're real happy with those, and I'll talk again about what might be some caveats when we sample other parts of the DMMA. And then for the physical, so the physical has a dual role. One, you want it to fit the ecological criteria of the salt marsh sediments, but there's also an engineering component that there are certain characteristics that won't really work in terms of the sediment handling. So we had to look at all of those. And in general, and again, Dr. Osborne's lab produced all of the results that you see here. In general, though, we show it from the DMMA sites, the same trend as in the salt marsh sites, that the highest proportion of grain size is sand, and next is silt, and next is clay. The DMMA had a lot more sand, higher percentage of sand, and a lower percentage of silt and clay than the other sites. Excuse my rough voice here. Moisture content, of course, the salt marsh has more moisture. I'm not even sure why we did that or why I'm showing it. But organic, and again, notice we got a little difference in scale here. The salt marsh sediments did show higher organic matter. We'll be able to clean that up a little bit by pulling from different dredge material management areas. Also, though, there's a lot of work from those summary guidance documents from the National Estuary Research Reserves that show that you can grow spartina in clay all the way to coarse and organic all over, and it grows. It's very forgiving. So we're not super worried about that. But in case, the beauty of the sediment, the dredge material management area is, and that's why I'm really glad we're looking at this as opposed to trying to sink our efforts with fine, is when they dump the material, the pipe is here, they pipe it from the intercoastal waterway and dump the sediment here, and then it spreads out. And the heavier, coarser sand material falls out here, and then you tend to get the very muckiest, silty material down there. So when we go back in, if we decide we don't want something that's so much sand and we want it to have a little silt or high organic, we can pull from this area and mix them. So we'll end up pulling this, putting them in dump trucks and kind of mixing it to create like a boutique sediment that matches the salt marsh.
Artisanal, right?
Exactly, artisanal.
Yeah.
I like
Yeah.
that. The other thing, though, the potential bad thing is when you have high organics, that's where you tend to see your higher PAHs and metals, because they absorb, those contaminants tend to absorb to organic particles. So we might start seeing, that was my caveat, we might start seeing higher hits of PAHs and things like that. But again, one of the things you can do with that is mix it with cleaner material to get the concentrations down, and then it's biologically appropriate. So we found sediment, we found a lot of it. We found it matches, has a good fit ecologically, a good fit for engineering design. But the next question is, how much do we want to add? Do we need to add? So we let the marsh kind of speak to us. And we went back to that data. And again, this was very coarse LiDAR data. We're going to clean this up in a phase 2. But we looked at the plots that had spartina, that had the highest density, really good looking assemblages, and looked at the elevation data. And we also paired that with the known tidal elevations where you tend to see Spartina alterniflora with what was at the site. And we ended up coming up with a target elevation of 1.66 feet. So we're going to take that sediment, and remember, we're going to add it back to the places which are now mud flat or oyster bar, and we're going to build it up so it's as high as the surrounding islands. And we're going to also add it to those drowning areas. And then finally, we want to put a layer over all of it, just as that little sea level rise bump for future sea level rise that we're going to see in the area. And this is what we end up getting, using our target elevation of 1.66 feet. And that's the mean high tide at this station. There's a great NOAA station right at the bridge there. That means adding 12 to 18 inches to the mud flats to bring them up to what those little Spartina islands look like. Adding another 3 to 6 inches to those areas within the salt marsh islands where we see the drowning. And then we were really conservative about the sea level rise one. We just added an inch because you don't want to convert your low marsh habitat to high marsh habitat. When you start doing that, you're going to end up getting colonization of species that are high marsh plants and not low marsh. We envisioned that, potentially what they could do is some sort of maintenance application over time. And then just adding an inch or two, every 5 years or so, just to try and keep up. So the estimated fill, and this ends up being just to recreate the footprint to 350 acres. This does not include adding to the drowning areas or the sea level rise, is about 270,000 cubic yards of material in all 8 of those zones to get it up, back up to where it was in the 1950s. Again, we're still in phase 2 is when we'll really dig into the techniques that we do envision a combination of the nozzle broadcasting technique as well as the pipeline. A lot of groups, especially if you're trying to recreate an island, they use coconut cores to hold in the sediment because you don't want it floating away. This is a tidal system. Lesson learned from the Army Corps. This picture on the left is from a project they did in Georgia, and they ended up not having any tidal flow outlets planned in this. And so it became saturated and ended up kind of going anoxic. And they ended up, I think actually a storm broke through one of those cores and ended up recreating the tidal and took care of the problem all by itself. So that saying nature bats last is applicable here. So some lessons learned about that, of maybe smaller bite-sized bits. There's a lot of structural analysis that needs to go on. How much of that material can those cores take without busting open? And then we'll really dig into some of the data that Dr. Angelini's group collected and will collect about the placement and orientation of the semi-permeable barriers in terms of where do we see a lot of that wake traffic and how best can we mitigate it. So project impacts. We're adding sediment right on top of salt marsh species. You would think that it was going to smother them. But if you noticed, we suggested that we would add, I think the most at 15 centimeters in those drowning areas. That actually fits really well with what other studies have shown. Spartina alterniflora can withstand and actually successfully begin colonizing and increasing density and all. So if you add less than 20 centimeters, you get positive effects. In this study, when they went above 20 centimeters, they saw negative impacts. 10 centimeters, nothing but positive. This study, 23 centimeters of sediment, positive impacts. Don't go above 60 though. 10 was good, 30 was good, 22 was good. So we've got a lot of precedence on what the species can actually take in terms of being loaded down with sediment. And all of these, except this one, were done at one time. So this one was done in 2 lifts. They added a little bit, waited a couple of months, came back. but they added a full 30 and a full 22 in one shot, and they still got positive growth, density, increased stem counts, increased height, whatever their metric was. Another thing we know that we're going to have to mitigate for is the habitat loss. We're going to be putting sediment on top of mudflat and sediment on top of oyster bar. By the way, this is that awesome aerial photography the drone took from that DEP did. Beautiful stuff here. We'll actually use this in if there's a phase 2 in when there's a phase 2, I'm gonna say, in quantifying that habitat loss and then mitigating that elsewhere. So we do know that that's going to be part of the story. And then of course, stormwater influence. We have residences and hospital, and they've got stormwater features, and they have discharge points within the marsh. We don't want to add sediment or back up those areas and cause flooding. So we did some just preliminary looking at the basins and nodes and channel. We'll do some H&H modeling to make sure that we're not affecting upland drainage. And then the next step will be final design. Earlier this year in July, we submitted with, again, Dr. Angelini as the lead PI, grant to NIFWIF for the final design phase and permitting, total budget of $1 million. And we'll get to do some more fun on the next phase. So happy to answer any questions. Yeah.
All right, let's give a round of applause. Thank you very much. All right, we'll start with questions in the room. I'll see if anyone online overcomes their digital shyness, which is always a problem. I'll let you all go first, though. Yeah.
And no question's a silly question, because I know I went over. I tried anytime there's an acronym to say
Shannon
it.
McMorrow. Yeah, okay, yeah.
Sean's wife,
Yeah.
exactly.
I'm gonna let it stew. I know you gotta take together 30 seconds before you're ready with a question, but
So when do you think you'll start filling in the marshes? Like, what's the tentative start date?
the
Right.
question is, when do you think you actually start doing the work on, getting the dirt on the ground?
Yeah.
Yeah.
So the next phase is just the final design, and that will probably take 2-3 years. We think the permitting is going to be difficult, and at that point, then we will apply for another grant to do the actual implementation. So I'm thinking a 6-7 year window from now. Yeah, maybe more like 7 or 8.
So it's a long time. And the last slide you showed, like, the next phase of design is $1 million. And $1 million is a lot, but I was just looking at 270,000 cubic yards. And even just, back of the envelope, just the dirt and moving the dirt, 10 million.
Yeah, well, that's
So-
usually 10%. The design is 10% of the construction.
Okay,
That's
and so
usually the
you
metric.
think the total cost would be on the order of, like, if you were to do all 100 acres, right, of replacement, like
Mhm.
on the order of like 50 plus
Right. It
million,
could.
right?
I have a feeling we will not get permission to do the whole thing at once. I think they're gonna want to see a test, a little pilot, like
Yeah.
take one of those zones. And that we'll get permission to do that, and then let's see what happens, and then later phase those in. And it might actually be better for the system to have one site and let colonization of critters and plants, and then
Mhm.
do another. It might make a lot of sense to do it in steps anyway. It's gonna be expensive.
Yeah.
Yeah, especially because we're hauling. That was one of the reasons why sinking the project with the fine dredging. You literally, there have been projects where they float a pipe down the waterway 12 miles long and pipe the slurry to the site. This is expensive because 18 miles away, you're filling up trucks, they're coming
Yeah.
down, they're dumping, you're putting it on a barge, and that part, that will be expensive.
Yeah.
The hauling.
I have a quick question. On the slide, shoreline, nutrients, right, for sediment around. So what about nutrients are there?
Tell me where I get
Say
to
it
the
again.
slide.
Perfect. The nutrients in the dredge material.
Sediments,
Yeah.
like,
And what's the question?
like, the sediments were collected for analysis, so you said, you find for if there is anything nutrient. And benzene, something like that. So
Yes, let me go back to that slide so you can. Sorry, this slowly. I'm gonna go one more, just so you know. So we analyzed all of these. these are petroleum projects, all the heavy metals that you tend to see, the benzene, there's a whole list that are called priority pollutants that are most common. But the only hits we got were arsenic and cadmium that exceeded thresholds or were found at all. And then the nutrients, we really just kind of wanted to get a feel for if they were in line with what we were seeing in the salt marsh, because that could cause algal blooms. So we were concerned about that. Did that answer the question?
Yes,
Oh, okay.
I was just asking, like wondering what nutrients were required.
Oh, yeah,
Yeah.
sorry. So total nitrogen, TKN, nitrate, nitrite, ammonia, and total phosphorus were the ones we tested for. Yeah.
So we actually did get a question from YouTube. It's a great one. So Alexandra asks, are there any plans to test out co-restoration techniques like adding mussels to harness positive interactions between marsh grass and other organisms? That sounds like something that would come from Angelini or Altieri. So I don't know who Alexandra is, but yeah, maybe, yeah, nice one.
It's their known to plume.
Yeah.
Well, actually, not so much that, but I know Dr. Angelini does have, and I think it's active on the ground, a project to add sediments at different depths and different kinds of sediments, and they're looking at the effects on the biota. So not just the Spartina, but crabs, macroinvertebrates, microinvertebrates, things like that. But I don't know about the adding the mussels, but that you know was one of the reasons that you love oysters and other bivalves, because of their filtering capabilities and stability. We do envision putting them at areas along the edge that could potentially help retain some of the sediments, as well as provide that additional habitat or mitigation.
Well, Christine's on, so maybe you want to share about that.
Yeah, sure. So there's a graduate student actually on the call too, Brittany.
Hey, Brittany.
So Brittany is actually leading some of the experiments focused on looking at the sensitivity of mangroves and salt marsh vegetation to different sediment depths, as well as different grain size distributions of the applied material. So I don't know if Brittany wants to actually, I mean, she could comment on what her experiments really focused on, but she's actually been sourcing material from the dredge material management area and experimentally doing these manipulations. And we have, in collaboration with a Dutch student who's planning on coming next spring, we'll be looking at the potential benefits of, co-transplantation of mussels with supporting the early establishment, especially of mangroves. This is a really fascinating location that's at the ecotone of salt marshes and mangroves. So there's this opportunity for a sort of assisted habitat expansion of mangroves, possibly as a result of the thin layer placement. So Brittany has some ideas and experiments in the works that are probing those types of dynamics experimentally. And that way we have an idea of what may play out over time with a full scale application that Jennifer's been explaining in this talk.
Hey, Brittany,
Hi everyone, I'm here. I'm here. My camera's not on because I am viciously ill at the moment, but I'm here. Yeah. So basically just to echo kind of what Christine said, my experiments, I've set up about 50 plots in a salt marsh on the East Coast near St. Augustine. And at the moment I've added different depths of sediment, so 15 and 30 centimeters. And we're collecting data on both invertebrate and vegetation responses, as well as soil and water chemistry. So I'm still working on processing a lot of that data, but it's been collected. So we'll see. For the most part, at the moment, it's just been a lot of death, but that's something that has been shown in prior studies. And then, it kind of takes a growing season and things kind of really bounce back pretty magnificently. So, yeah.
Okay, Brittany, well, you'll be on for the wetland seminar maybe in next fall or something. Okay. Yeah.
Maybe, and hopefully not sick.
Yeah, Jennifer has a question for you.
I have a question for you, Brittany. So how long do you plan to monitor the sites after the application? To hopefully catch that.
I don't have an end date for monitoring. I'm really looking forward to next growing season. So next summer though, because we went and to the site last week, I believe it was, and we already saw, like mangrove propagules in some of the plots. And so I'm really interested to see next growing season kind of how that pans out, and how the spartina, if they bounce back as well. But I don't have an end date for now. I think that this is something that I could kind of play with over time. And, even if I want to do something like, instead of just looking at recolonization, adding species for colonization as well. So whether you plant mangroves, add spartina, add mussels, as someone suggested. So I think that there's a lot of room for things to happen.
Give it a
Thanks,
jump
Brittany.
start.
One question.
Yeah.
You said you did a sample on the volume of the sediments, yes? I wanted to know which part of this deposited sediment in the surface, inside this volume, because I did my master on the stabilization and fabrication of the dredged sediment.
Mhm.
And I knew that when there is a volume of the sediment, it can be washed the heavy metal and other pollutant with the water that rained. And it can go from the surface to inside the volume or in the down part of the volume.
Right,
I want to know, you did a sample in which part, because you said this sediment is from the navigation channel,
Mhm.
and it should be how some heavy metal like lead and something like this. I'm wanting to know, you did in the down part or inside this volume or not?
right. So the question is, did we go down deep enough to capture if there's leaching occurring down? And you were surprised by the results that you didn't see heavy metals. Exactly. So first of all, let me point out, in Florida, we tend not to have high industrial facilities. So you don't, like in the Northeast, where you have plants that are emitting mercury or other heavy metals, we tend not to have that kind of industry. So what we tend to see in Florida are the byproducts of wood burning plants from atmospheric. Mercury is all over the place. I was really surprised we didn't find mercury. Boat places where they use copper to defoul the bottom of the boat, you'd expect that, but we don't have those big nasty industries that are leaching water into petroleum's a big one that you'd expect to see. But to your point, yeah, our budget was such that we could only dig down 3 feet. When we go to phase 2, we'll take drill rigs into here. We will go down to the very bottom and take out an entire column of soil, and we'll stratify it, and we'll send off the top and send off the middle, and we'll get a stratification analysis through that entire length that represents the total depth. And we'll also go to these different areas because we know this is the siltier, more highly organic, and that's where you're going to find the nasties like the PAHs and all that are absorbing to the organic. So exactly, that was a flaw here, and we just didn't have budget to do that, bring in those drill rigs. And yeah, that's why I say we're gonna find some other hits on the chemical analysis later for sure. Good question.
So zooming out like 100 miles from that, like, so this is, in Florida, beaches erode and we do beach nourishment. And then here we have like an ecological system that is in transition, partially because of human effects and partially just because of sea level rise and drowning. And so you said like, well, maybe we'll just come back and do this every 5 years. And so I guess maybe what's your take on this idea of marsh, like assisted marsh survival
Right.
via sediment dredge placement, like as a long-term, this one little chunk, it's going to be a couple $1 million. It's maybe over a couple years, and it's going to be something where we're going to go and place all this material and try to save all the marshes. Are we gonna how are we gonna prioritize it? Are we gonna
Right.
garden these systems forever until we have to move? Like, what's the long-term?
Right. Well, I think there's a little bit too that if we can stop. So a couple of things are probably happening here, and it's a positive feedback loop. I think when you stop those erosional effects, first of all, and you start getting that progradation, you're gonna see accretion just occurring naturally. So we're gonna see buildup that has nothing to do with the fact that we added sediment. I also mentioned we are thinking about that we might be planting plants as well in the next phase instead of just letting stuff colonize. And as soon as you put plants in, again, you increase the rate of accretion in those sets. So there's a little bit of that just by building it, you create a positive loop where you're just going to get stuff stacked up more. But I think that with sea level rise, we may have to do that maintenance stuff, unfortunately. But it might not be to the degree that we have to. To 14 inches or whatever. And I did just want to show real fast. At that point, once we kind of built up, sorry, I wish I had a faster way.
Yeah.
These sites are going to the navigational channels almost there. The navigational channels will always have to be dredged.
Yeah.
And here. And at this point, once we build this up, it might be that we can, as they're dredging here, they have a
Just spray it.
nozzle and they're
Yeah.
going and just spraying stuff back on top of them. So it might not be as expensive. It can time with their navigation and dredging activities. And hopefully it would get permitted. So
Just
like
be
a general
consistent,
permit, yeah, and you don't have to go through it every time. So it might not be as big a deal, but I think it's gonna be a combination that just by restoring it somewhat, you're just gonna start seeing that accretion naturally. But I think too, we need to have conversation, and I've talked to Christine about this, but we need to bring in other folks to really talk about that effect of the boat wakes. And, you hate to ruin people's fun, but are there certain zones where we know that it has really bad effect? And should those be like no wake or at least slow down or something like that? Because that's a big part of it too, that's going to just continue whether they're semi-permeable barriers or not. Yeah.
All right, well, we're at time, so, yeah, go ahead.
I want to know if you did any action to reduce the concentration for the two components, the arsenic and the candium.
Well, those actually, the high hits were in the salt marsh itself. So not our donor material. So, but if we did get hits in our donor material, there are ways that you can mix it with cleaner material to get the concentrations down. And that's probably what we would do. Or not use that bad part at all. Stay away from that area. We're not using it.
Christine, any last comments? I see your video is on, or you just want to say?
I'll just say, I mean, my fingers are crossed. We should know in early December if we're going to be able to move forward with the sort of final design phase of this project, which is really exciting. This is the opportunity for like translation of fundamental science. We're doing to translation and like real world application. So it's really exciting to see that there's this opportunity to really like actually do restoration at a fairly significant scale. And I think we're there because of the partnership between an academic university and an environmental consultancy that is well managed by somebody like Jennifer. So it's been a really great experience to collaborate with them and have this like flow of information back and forth. And there's a lot that they're offering that we just can't do ourselves or don't have the skill set or the, to approach. And so this is really, I think, generally this highlights the value of interdisciplinary cross-sector types of collaboration to make progress. So thanks a lot, Jennifer. It's been so fun to work with you. And
We'll say
yeah.
we're working with Christine as well and her team. Yeah, and it is a nice complement of skill sets and big picture details, all of that. Yeah, fingers crossed for us.
All right, we'll have you back for the next round.
Okay,
Okay,
there we
thanks a
go.
lot, Jennifer.
Thank you.
Appreciate it. All right, good to see everyone on YouTube and out in the world. Let's see, next week, we'll see you again next week, and still until then, stay safe with the storm. See you later.